Good afternoon, everyone. My name is Ștefănică Elizavizitiu. I'm from the Faculty of Civil Engineering and Building Services from Gheorghe Asache Technical University of Iași. And today I'm going to present an experimental research on a heat pipe-based waste heat recovery and storage system, a water-to-water waste heat recovery and storage system, that employs phase change material for energy recovery and storage. Looking at the current global energy landscape, we can see a strong shift towards sustainability in recent years. The Paris Agreement marked an important moment where almost all nations aimed together at limiting the global warming below 2 degrees Celsius. And around the years, there were a lot of set of policies and legislative measures that raised the renewable energy targets in order to become carbon neutral by 2050. Romania also is aligned with these goals by raising its renewable targets to 30.7%. 48% of the energy demand is consumed as heat, and 29% of the greenhouse gas emissions is represented by the industry. In this context, heat recovery and storage system can play an important role to promote a sustainable future. The aim of this research is to experimentally investigate and validate the performance of a novel heat pipe-based waste heat recovery and storage system utilizing paraffin RT44HG as a phase change material. The system aims to recover, store, and utilize thermal energy while addressing the dual challenges of efficient heat recovery and storage in various applications. Among the key goals are to quantifying the effectiveness of the novel system, to analyze the thermal storage and transfer performance of the PCM, and to experimentally validate the integration of heat recovery and storage within a single compact unit, and also to explore the immediate applications of this system. Here we have the 3D model of the novel dual waste heat recovery and storage system. This comprises two principal zones, the evaporator and the condenser, which is separated by a sealing flange that acts both as a sealer and a divider. Looking closer at the condenser, we can see here two zones labeled as A and B. In the inner zone A, there is a secondary agent, which is water from the water network supply that fills in this zone. Also, we have 20 evenly distributed heat pipes within this area that promotes instant hot water. At the same time, in zone B, in the outer zone, we have the phase change material, the paraffin, and also 18 heat pipes that transfer the heat to the PCM, initiating the melting process. The secondary agent heated into the inner zone can be rerouted through a coil which is embedded within the PCM in order to extract the thermal energy stored within the PCM. Also, the primary agent from which the heat is extracted, which flows through the evaporator, is water. In our experimental, it was water generated by an 8 kilowatt electric heater. Here we have also the schematic of the and the functionality of our system. And here is a picture from the stand in our laboratory. The temperature is monitored by 9 type K thermocouples, which are placed in the inlets, outlets, and also along the PCM from the base to the top. And the temperature are registered by an electronic thermometer. Also, in order to prevent the heat losses, 10 centimeters of mineral wool was chosen. We employed a total of 10 experimental tests, as we can see here, And while varying various parameters, such as the primary agent temperature, which was varied between 50 degrees to 70 degrees Celsius, its flow rate remained constant at 22 liters per minute. The secondary agent flow rate was also varied depending on the test, from 1 to 3 liters per minute, and the duration ranged from 3 and 4 hours. The secondary agent, being the water from the water network supply from our laboratory, had slight variations, and also the tests were performed in the summer. We divided the experiments into 3 stages: a melting, a heating, and a cooling stage. In the melting stage, the valves for the secondary agent were closed while the electric heater was turned on in order to focus all the thermal energy towards melting the paraffin. In the second stage, the valves were open, allowing for the secondary agent to circulate through our system and to generate instant hot water. In the third stage, the cooling stage, the electric heater was turned on, allowing for the secondary agent to absorb the thermal energy stored within the PCM. For the analysis, we grouped the test based on the parameter varied, and here we can observe the sensors which were placed in our system. For the first test, this served as a baseline scenario, which was conducted without insulation, and validates the fact that the insulation promotes both a better melting, a faster melting, and also higher temperatures in the secondary agent. Group B focused on the analysis of the primary agent variation. The primary agent was varied between 60 and 70 degrees, while keeping a 3-hour duration test. This test 8 performed the best. This demonstrates that having a higher primary agent temperature results in more sustained temperatures within the PCM and also the secondary agent. Group C focused on also on varying the primary agent temperatures, but having a duration of 2 hours of melting. And also we employed a case with 50 degrees for the primary agent. This was notable and validated that our system can effectively recover thermal energy even with a lower primary source. Group D and F focused on varying the primary agent temperatures at 60, 65, and 70 degrees. And with a duration of 3 and 4 hours. This demonstrates that extending the melting phase is very important, because as we can see, in the melting, heating, and cooling stage, we had the highest temperature in the 4-hour duration tests. The last group focused on varying the flow rate for the secondary agent to 1, 2, and 3 liters per minute while keeping the primary agent temperature constant. As we can observe the temperature of evolution of the PCM, we had the highest temperature in the PCM in the case employing the lowest flow rate. This also demonstrates that the system performs best with lower flow rates for the secondary agent and higher temperatures. In terms of efficiency and performance, here we can see some graphs with the temperature gains in the heating and cooling stages. From the 4-hour duration test 10, which employed 70 degrees for the primary agent, performed the best, gaining 34.3 degrees Celsius during the heating stage and 11.3 degrees in the cooling stage. And in the 3-hour duration test 7, which employed 1 liter per minute and 70 degrees for the primary agent, had the best results. In terms of efficiency, again, test 7 had the best efficiency of 86%, while test 2, employing 50 degrees for the primary agent, has also notable results. As conclusions, the inclusion of insulation enhances the thermal retention and also increasing the primary agent temperature along with extending the melting phase from 1 to 2 hours and lowering the flow rates prove to be optimal for the system. The system's average efficiency varied between 65 and 86%, which demonstrate its robust thermal recovery capabilities. Before going to the potential applications, it's important to note that this system captures thermal energy from low temperature sources. It utilizes high efficiency heat pipes for almost instant hot water production. It incorporates paraffin as a phase change material, and it has a dual functionality within a compact and efficient unit. This system can be utilized in the residential use, where it recovers thermal energy from the hot water produced by solar thermal panels, by the excess thermal energy, which has an average of 50 degrees Celsius. In this way, we can reduce the energy required for domestic hot water preparation, and also we have the ability to store the captured excess heat for short-term use. And in the industrial use, it can be used in the pulp and paper industry, textile, dairy, or in the food processing industry, where the thermal energy can be recovered from various wastewater sources, from various processes. We can use the thermal energy for preheating boiler feed water, pre-rinsing equipment, and also we are able to store the excess heat in order to reduce the energy waste and contribute to industrial sustainable practices. Thank you for your attention.